Hello, friends. Disclaimer. As an Amazon associate, I earn from qualifying purchases at no additional cost to you. Please don't forget to check out product links for stargazing in the description of the video. With the Artemis program paving the way for humanity's return to the moon, the need for a permanent lunar base is more pressing than ever. But there's a problem. Transporting construction materials from Earth is not just expensive, it's logistically challenging and inefficient. Each kilogram of material launched from Earth requires meticulous planning and adds to mission costs, making a sustainable presence on the moon nearly impossible using traditional methods. To overcome this, scientists are exploring ways to use local resources found on the lunar surface. Enter microwave sintering, a groundbreaking technique that could allow us to build structures directly from lunar soil. Microwave sintering might seem like a niche technology, but it's at the heart of some of the most cutting-edge research in space architecture today. By harnessing the power of microwaves, this process can solidify lunar soil, known as regolith, at temperatures far below its melting point, turning it into sturdy bricks. These bricks could then be used to construct habitats, landing pads, and other essential infrastructure on the moon. But what makes this technology truly remarkable is that it leverages materials already available on the moon, drastically reducing the need for Earth-based resources. So, how exactly can lunar soil be transformed into solid building blocks? And what unique properties of moon minerals make this possible? In this video, we'll explore the science behind microwave sintering and how it's being developed to turn the moon's regolith into strong, durable bricks suitable for constructing a lunar base. We'll take a closer look at the research being conducted by institutions like NASA, the European Space Agency, and the Korea Institute of Civil Engineering and Building Technology. The potential of microwave sintering goes beyond just construction. It's a key enabler for sustainable lunar exploration, reducing the need for costly Earth-based materials and paving the way for future space architecture. With each passing day, the dream of building a self-sustaining lunar base moves closer to reality thanks to advances in material science and microwave technology. And as the science progresses, what was once considered a distant vision is now within humanity's grasp. Building a base on the moon is no small feat. The concept sounds simple. Construct habitats, landing pads, and research stations. But when you factor in the harsh lunar environment and the sheer logistics of getting materials there, it quickly becomes a daunting challenge. One of the biggest hurdles is the cost of transporting construction materials from Earth to the moon. Every kilogram sent into space carries a hefty price tag. Rockets have limited payload capacity, and even with the advances in space technology, the expense of hauling heavy building materials is astronomical. NASA's Artemis program aims to establish a sustainable presence on the moon, but doing so entirely with Earth-based resources is neither practical nor affordable. This is why the focus has shifted to using materials already available on the lunar surface, specifically lunar regolith. Lunar regolith, the loose soil and dust that covers the moon's surface, might not look like much, but it holds the key to unlocking a sustainable lunar base. However, using this material comes with its own set of challenges. Regolith is made up of tiny, sharp-edged particles that can be difficult to handle and process. It lacks the cohesive properties of traditional construction materials like concrete or bricks. To make it suitable for building, scientists need to find a way to transform this loose soil into solid, durable structures. This is where the process of sintering comes in. Sintering involves heating the material to just below its melting point, causing the particles to fuse together. But how do you achieve this on the moon, where temperatures swing between extreme highs and lows, and traditional construction methods are impossible? Researchers have explored various options, including using lasers and solar energy to heat the regolith. But these methods come with their own limitations. Lasers require precision and a significant energy supply, while relying on solar energy depends heavily on the lunar day-night cycle, which spans 28 Earth days. Enter microwave sintering, a promising solution that could overcome many of these challenges. Unlike other methods, microwaves penetrate deep into the material, allowing for even heating. This is particularly important when dealing with regolith, as its composition can vary greatly depending on location. Microwaves can be tuned to specific frequencies that interact with the regolith's dielectric properties, making the heating process more efficient. By using microwaves to sinter the regolith, scientists can create solid building blocks that have the strength and durability needed for a lunar base. But even with microwave sintering, there are hurdles to clear. One of the major challenges lies in understanding the precise properties of lunar regolith and how it interacts with microwaves. Lunar soil is different from anything we have on Earth, so scientists use simulants, materials that closely mimic the composition and behavior of real lunar soil. These simulants allow researchers to test and refine their techniques before applying them on the moon. However, even the best simulants can't perfectly replicate the complexities of real lunar regolith, which means there's still a degree of uncertainty when it comes to scaling this technology for actual lunar construction. Another challenge is the need for efficient energy use. While microwave sintering is more efficient than other methods, it still requires a reliable power source. Establishing a stable energy supply on the moon is crucial for the success of any long-term base, and integrating that with construction processes adds another layer of complexity. Current research is exploring how to integrate renewable energy solutions, such as solar panels or nuclear power, to provide the consistent energy needed for microwave sintering on a large scale. Despite these challenges, the progress made in recent years is promising. Scientists are getting closer to overcoming the technical barriers, and every breakthrough brings us one step nearer to realizing the dream of a self-sustaining lunar base. The next step is turning these laboratory successes into real-world applications on the lunar surface, a transition that will mark a monumental leap in human space exploration. When it comes to building a lunar base, traditional construction methods simply won't work. The moon's extreme environment, ranging from freezing cold to scorching heat, poses unique challenges that Earth-based techniques can't easily overcome. That's where microwave sintering comes in, a cutting-edge technology that could revolutionize lunar construction by turning local soil into solid building blocks. So, what exactly is microwave sintering, and why is it so promising? Let's break it down. At its core, sintering is a process where powdered material is heated to just below its melting point, causing the particles to fuse together. On Earth, sintering is commonly used in industries like ceramics and metallurgy to create strong, durable materials. On the Moon, the concept is similar, but instead of using conventional heating methods, scientists are turning to microwaves. Microwave sintering works by using electromagnetic waves to heat materials from the inside out. Unlike traditional heating, which applies heat externally and gradually warms the entire material, microwaves penetrate deep into the material, causing the particles to vibrate and generate heat. This allows for faster and more uniform heating, making it ideal for processing lunar regolith, which is a mix of fine dust and rock fragments. But why microwaves? The answer lies in the unique properties of lunar regolith. The soil on the Moon is vastly different from anything found on Earth. It's composed of tiny, sharp-edged particles that are rich in metals like iron, silicon, and titanium. These materials have specific dielectric properties, meaning they interact with microwaves in a way that allows for efficient heating. Unlike Earth-based soils, which might reflect or absorb microwaves unevenly, Lunar regolith is more responsive, making it an excellent candidate for this technology. The process begins with gathering lunar regolith, either manually or through robotic systems. Once collected, the regolith is fed into a chamber where it's exposed to microwaves at a specific frequency. The dielectric properties of the regolith cause it to heat rapidly, reaching temperatures high enough to fuse the particles together without completely melting them. The result is a solid block of material that can be shaped into bricks, tiles, or other construction elements. But microwave sintering is more than just a convenient way to make bricks. It's a key enabler for sustainable lunar exploration. By using local resources, it dramatically reduces the need for transporting building materials from Earth, which is not only costly, but also limits the scale of lunar construction. With microwave sintering, it's possible to build larger, more complex structures directly on the Moon, paving the way for habitats, laboratories, and even landing pads that could support long-term human missions. NASA and its international partners, including the European Space Agency, ESA, and the Korea Institute of Civil Engineering and Building Technology, are leading the charge in developing this technology. Each organization brings its own expertise to the table, from understanding the material properties of lunar regolith to designing microwave systems capable of operating in the harsh lunar environment. One of the most promising aspects of microwave sintering is its adaptability. The process can be fine-tuned to work with different types of lunar soil, which varies in composition depending on location. For example, highland regions on the Moon are rich in silicon and aluminum, while mare regions contain more iron and titanium. By adjusting the frequency and power of the microwaves, scientists can optimize the sintering process for different soil types, ensuring that construction is possible across a wide range of lunar terrains. The role of ilmenite, a mineral rich in iron and titanium, has been a major focus of recent research. Ilmenite is abundant on the Moon, particularly in the mare regions, and its unique crystal structure makes it highly responsive to microwave heating. When mixed with regolith, ilmenite acts as a catalyst, enhancing the efficiency of the sintering process and allowing for faster, more uniform heating. This has significant implications for lunar construction, as it means that building materials can be produced more quickly and with less energy. KICT's research team has been at the forefront of this effort, conducting detailed studies on the dielectric properties of lunar regolith simulants and ilmenite. By replicating the conditions found on the Moon, these scientists are able to test how different mixtures of regolith respond to microwave sintering. Their findings have revealed that, while pure lunar regolith can be difficult to heat efficiently, the addition of ilmenite greatly improves the process, making it possible to create bricks with a strength comparable to concrete. However, this technology is still in its early stages. While laboratory tests have shown promising results, scaling up microwave sintering for actual lunar construction presents several challenges. One major hurdle is power generation. Operating a microwave system capable of sintering large volumes of regolith requires a stable and continuous energy supply, which is difficult to achieve on the Moon. Current research is exploring how renewable energy sources like solar panels could be integrated into the sintering process, providing the necessary power while minimizing environmental impact. Another challenge is the design of the sintering equipment itself. On Earth, microwave systems are large, stationary machines. But on the Moon, equipment needs to be compact, lightweight, and capable of operating autonomously in a remote and harsh environment. NASA and its partners are working on developing robotic systems that can handle both the collection of regolith and the sintering process, reducing the need for human intervention. The ultimate goal is to create a fully automated system that can continuously produce building materials directly on the Moon. Such a system would be a game changer, enabling large-scale construction without the need for constant resupply missions from Earth. This would not only support the establishment of a permanent lunar base, but also serve as a testing ground for future missions to Mars and beyond, where similar challenges of resource scarcity and extreme conditions are expected. As the research progresses, the vision of a lunar base built using microwave sintering is becoming increasingly tangible. The ability to construct habitats, roads, and other infrastructure directly from lunar soil would mark a significant leap forward in space exploration. It represents a shift from merely visiting the moon to truly living and working there, a key step in humanity's journey beyond Earth. In the next few years, we're likely to see prototype systems tested on the moon, laying the groundwork for more permanent settlements. The work being done today is turning what was once science fiction into a realistic and achievable goal. As we push the boundaries of technology and expand our presence in space, microwave sintering could be the foundation, literally, of humanity's future on the moon. The concept of building a lunar base using local materials isn't just a futuristic dream. It's backed by extensive research and scientific breakthroughs. Multiple institutions across the world are working tirelessly to bring this vision to life, with microwave sintering emerging as one of the most promising techniques. Let's explore the key research driving this technology forward and the significant milestones that have been achieved. NASA, the European Space Agency, and the Korea Institute of Civil Engineering and Building Technology are at the forefront of this research. NASA has led studies on lunar regolith properties and how they interact with energy sources like microwaves, while ESA focuses on developing automated systems capable of handling large-scale sintering operations on the moon. KICT, meanwhile, has been instrumental in understanding the dielectric properties of lunar regolith simulants, an essential factor for optimizing microwave sintering. One of the major challenges in microwave sintering is the variability in lunar soil composition. The moon's surface isn't uniform. Different regions have different types of regolith, each with unique properties. This variability can affect how the soil responds to microwaves, making it essential to understand the dielectric properties of regolith across different lunar locations. To address this, KICT conducted in-depth studies using a lunar simulant known as KLS-1, which closely mimics the properties of real lunar soil. Their research has provided crucial insights into how regolith behaves when exposed to microwaves at different temperatures, laying the groundwork for more efficient sintering techniques. A significant breakthrough involves ilmenite, a mineral abundant on the moon. Ilmenite's unique crystal structure makes it highly responsive to microwave heating. By mixing ilmenite with lunar regolith, scientists can enhance the sintering process, achieving faster heating and stronger bricks. This discovery is a game changer for lunar construction, especially in mare regions rich in ilmenite, which could become ideal sites for establishing bases. Lab tests have shown that adding ilmenite to lunar regolith simulants results in bricks with a strength of over 20 megapascals, comparable to concrete. This level of strength is essential for ensuring that lunar structures can withstand extreme environmental conditions, including drastic temperature fluctuations and potential micrometeorite impacts. These breakthroughs show that microwave sintering is not just a theoretical concept, it's a practical method for creating robust construction materials from lunar soil. Another key area of research involves optimizing microwave frequencies. The efficiency of microwave sintering depends heavily on tuning the frequency to match the dielectric properties of the material being heated. Through extensive testing, researchers have identified the ideal frequencies that maximize energy efficiency while ensuring even heating. This is critical on the moon, where energy sources are limited and need to be used as efficiently as possible. International collaboration has been vital in advancing this technology. NASA's partnerships with institutions like ESA and KICT highlight the global effort to develop sustainable lunar construction methods. By pooling resources, expertise, and data, these organizations are speeding up the timeline for bringing microwave sintering to the Moon. This collaboration also involves creating standards and protocols to ensure the technology is consistent and reliable across different missions. However, challenges remain. Scaling microwave sintering from controlled lab environments to the unpredictable conditions of the lunar surface is a complex task. Ensuring consistent brick quality in large production runs and deploying automated systems for regolith collection and processing still require further refinement. Despite these hurdles, significant progress has brought us closer than ever to using local materials for building a sustainable lunar base. The next steps involve testing prototype microwave sintering systems in actual lunar conditions. NASA and its partners plan to conduct field tests in upcoming lunar missions, which will be critical in validating the technology and identifying any remaining obstacles before full-scale implementation. As these systems are refined, the vision of a lunar base built from Moon soil moves closer to becoming reality. As we continue to explore the potential of building a lunar base using local materials, one key resource has emerged as a critical element in the process: ilmenite. This mineral, abundant on the Moon, is proving to be a game-changer in the microwave sintering technique. But to fully understand its importance, we need to dive deeper into what ilmenite is, why it's significant, and how lunar simulants are helping scientists perfect this technology before it's deployed on the Moon. Ilmenite, scientifically known as iron titanium oxide, is found in large quantities on the lunar surface, particularly in the Moon's mare regions, those vast plains formed by ancient volcanic activity. These regions are rich in basaltic rocks that contain high concentrations of ilmenite. On Earth, ilmenite is primarily mined for its titanium content, which is used in everything from aircraft manufacturing to paint. But on the Moon, ilmenite's unique properties make it a valuable resource for a completely different reason: its ability to efficiently absorb and convert microwave energy. The crystal structure of ilmenite is highly responsive to microwave heating, allowing it to reach high temperatures quickly. When mixed with lunar regolith, ilmenite acts as a catalyst in the sintering process, enhancing the efficiency and uniformity of the heating. This means that bricks and other construction materials can be produced more quickly, with less energy required. The presence of ilmenite in certain lunar regions could also influence where future lunar bases are established, as regions rich in this mineral will offer a natural advantage for building materials. However, studying and perfecting this process on Earth presents its own challenges. The lunar environment is unique, and while we can't exactly replicate it here on Earth, scientists have developed lunar simulants, materials designed to mimic the properties of real lunar soil. These simulants are crucial for testing microwave sintering techniques before they're used on the Moon. One such simulant is the Korean Lunar simulant, developed by the Korea Institute of Civil Engineering and Building Technology. KLS-1 closely resembles the chemical composition and physical properties of lunar regolith, making it an ideal material for laboratory experiments. Researchers use KLS-1 to study how different mixtures of simulant and ilmenite behave under microwave sintering. This allows them to refine their techniques and gather valuable data on how the real regolith might perform when exposed to the same conditions. The research conducted using these simulants has already led to important discoveries. For instance, while pure lunar regolith is microwave transparent, meaning it doesn't heat efficiently, adding ilmenite dramatically improves its response to microwaves. The ability to control and optimize the dielectric properties of the regolith mix is key to creating strong, durable building materials. The results from these tests show that the inclusion of ilmenite can produce bricks with the structural integrity needed to withstand the harsh lunar environment, including temperature extremes and impacts from micrometeorites. These findings are shaping the future strategies for lunar-based construction. By targeting regions with high ilmenite concentrations, space agencies can maximize the efficiency of their building processes. This approach not only reduces the amount of energy required, but also speeds up construction timelines, making it more feasible to establish long-term habitats on the Moon. In addition to structural applications, ilmenite could also play a role in supporting other aspects of lunar exploration. The mineral is rich in oxygen, which could potentially be extracted and used for life support systems or as an oxidizer for rocket fuel. This makes ilmenite a multi-purpose resource that could contribute to both construction and sustainability on the Moon. As promising as this research is, the true test will come when these techniques are applied in situ on the lunar surface. The success of microwave sintering, combined with the strategic use of ilmenite, could transform how we approach building in space, turning the Moon's natural resources into the foundation for a permanent human presence. As we look ahead to humanity's return to the Moon, the possibilities unlocked by microwave sintering and the strategic use of lunar resources like ilmenite go far beyond simply building habitats. This technology could revolutionize every aspect of lunar exploration and lay the groundwork for future missions to Mars and beyond. Let's explore how these developments could shape the future of space exploration. The primary application of microwave sintering is constructing essential infrastructure, from habitats and landing pads to roads and storage facilities. By using local materials, space agencies can drastically reduce the costs and logistical challenges associated with transporting construction supplies from Earth. This self-sufficiency is critical for establishing a sustainable lunar base and for creating a model that can be adapted for other celestial bodies, like Mars. Beyond infrastructure, microwave sintering could also be used to create protective barriers against the Moon's harsh environment. Structures built using sintered lunar regolith offer enhanced protection against micrometeorites and extreme temperatures, ensuring the safety and longevity of equipment and habitats. An exciting prospect is the development of modular construction techniques. Sintered bricks and tiles can be mass-produced and assembled like building blocks, allowing for flexible expansion of a lunar base. As the base grows, advanced facilities such as laboratories and greenhouses could be added, supporting research, food production, and resource extraction. Ilmenite's role in lunar construction extends beyond building materials. As a source of oxygen, ilmenite could support life support systems and fuel production, moving us closer to a closed-loop system where resources are generated on-site. Looking further ahead, the technology perfected on the Moon could be adapted for use on Mars. Mars has its own version of regolith and mineral resources that could be processed similarly, paving the way for a human presence on the red planet. The lessons learned from lunar construction will provide valuable insights for building in even more remote and hostile environments. The future of lunar exploration is filled with possibilities. As we transition from exploratory missions to permanent settlements, the technologies being developed today will be instrumental in turning these visions into reality. Microwave sintering, combined with the use of ilmenite and other local resources, is a major step toward establishing a sustainable human presence on the Moon, and eventually beyond. We've explored the cutting-edge science behind turning the Moon's resources into the foundation for humanity's future in space. What was once the stuff of science fiction is now on the brink of becoming reality. With microwave sintering, we have the potential to build infrastructure on the Moon using nothing more than lunar soil and minerals like ilmenite, reducing our dependence on Earth and opening the door to long-term lunar exploration. This technology represents a significant leap forward. By leveraging the unique properties of lunar regolith and optimizing the sintering process, space agencies can construct habitats, landing pads, and research facilities right where they're needed, without relying on costly shipments from Earth. The role of ilmenite as both a building material and a source of oxygen adds even more value, making it a cornerstone of future lunar missions. As NASA's Artemis program and its international partners prepare for humanity's return to the Moon, the research being done today is laying the groundwork for the next giant leap. The strategies and techniques developed for lunar construction could set the stage for even more ambitious goals, like sending humans to Mars and establishing permanent colonies in deep space. The Moon is our testing ground, and success here will pave the way for the next frontier. But this is just the beginning. Over the next few years, we'll likely see the first real-world applications of microwave sintering on the lunar surface. These tests will determine if the theories and experiments conducted in labs can translate into practical solutions in the harsh conditions of the Moon. As we get closer to these milestones, it's clear that we're entering a new era of space exploration, one where we don't just visit other worlds but build and live on them. If you're fascinated by the advancements in space technology and want to stay updated on humanity's journey beyond Earth, make sure to subscribe to our channel. We'll be following the developments closely and bringing you the latest insights from NASA, ESA, and other space agencies as they turn this vision into reality. Remember, the future of space exploration is not just about reaching new destinations. It's about creating a sustainable presence that will allow us to explore deeper and stay longer. With innovations like microwave sintering, the dream of living and working on the Moon is closer than ever before. If you're ready to take your space knowledge to the next level, check out the telescope and binocular through the links in the video description below. As an Amazon associate, I earn from qualifying purchases, but it won't cost you a penny extra. Thank you for joining us on this journey through Lunar Base. Please like, comment, and share the video, and please do not forget to subscribe for more videos.